In our look at the new features of C# 9, the next thing I wanted to talk about was a new language construct known as a record. But in order to fully understand the benefits of this, we need to get to grips with a much more fundamental feature within C# memory management, which is the idea of value types and reference types. Maybe something you've covered before, in which case you can skip this, but we really need to get to grips with it, not just for records, but for all sorts of other things in terms of writing efficient C# code. So what we have when we have types in C# are these two fundamental concepts, the value type and the reference type. And if we think of these in terms of what we get built into the language, things like numbers, things like integers and doubles and that sort of thing, those are what are known as value types, whereas things like strings or arrays are things that are known as reference types. And I think immediately you'll be able to spot the key difference between them in that value types have a fixed size. There is a fixed number of bits required to store an integer, 32 bits, whereas reference types tend to have variable size. So a string could be any length, an array could be any length, and that's one of the key things that gives us the decision between them. Now in C#, as programmers, we also write our own data types, and we get the choice as to whether we're going to have value types or reference types. If we want to write a reference type, which is actually what we do most of the time, we use the keyword class, but if we want to write a value type, then we use the keyword struct. And so what I've got to show you here is an example of both of those. So as a value type, I've got this point, and all we've got is it's got an x coordinate and a y coordinate, both of them ints. It's just got a toString so we can display it, and then some stuff I've commented out that we'll see later on. So that is a struct and therefore a value type. And then we've also got, as a reference type, we've got a person base class, so that's declared as a class. There we've got person again with a toString. And then, as we'll see later on, we're also using a couple of derived classes. So a customer is a kind of person and an employee is a kind of person. So all of that structure, that is reference types. But let's start out with value types. And let's just go to our program. And what we're going to do here is in CreateObjects, I'm simply going to declare a point that I'll call p1 equals new point, and then just use the member initializer to give it some values. Now what's happening in terms of memory here is this. In C# memory, we have two areas of memory. It's actually a bit more complicated than this, but this is sufficient for our purposes. We've got these two areas of memory that we can display like that, and we call one area the stack and the other area the heap. And although these two are both memory that we've got on our system, they are managed in slightly different ways. If you've got a value type, a struct, like we have here, then it likes to live on the stack. That's its natural place to live. Whereas if we've got a reference type, its natural place to live is on the heap. So when we declare point p1, all that happens is that data with the two values x and y is allocated at the next available slot on the stack. And that slot is indicated using what is known as the stack pointer. So we allocate enough memory for two integers, which is what a point contains, and that's 64 bits. And when that's done, the compiler knows that those objects are 64 bits in size, and so it moves the stack pointer up by 64 bits. If we then had another point, then it would again be allocated on the stack at the next available slot, and so the stack pointer would know exactly where to put it and then would move up and the next one would go in, and so on and so forth. And the key thing about this is it's very efficient because all of that is handled by the compiler, because the compiler knows how big these objects are. When we then go out of scope, so when we go through that closed curly brace on the CreateObjects, then anything on the stack created within the scope of those curly braces is automatically deallocated. And in fact, the way it's automatically deallocated is very simple. The stack pointer just drops back to the location on the stack that it was at when it came into this function. So actually there's no real memory deallocation at all. Those points are still there on the stack, they're just inaccessible. And so now, if back in main, for example, I put something else on the stack, then all that happens is it just overwrites what was already there. So point P1 and P2 are effectively deleted. We don't need to tidy up because they'll just get overwritten as this goes along. And because the vast majority of the work of this mechanism is handled by the compiler, there's very little work done at runtime, and that makes it a very efficient system. On the other hand, let's see what happens when we're dealing with classes. So let's now here say person Fred equals new person, and then just give them a name of Fred. Now what's happened here is rather different. The variable Fred is still something that goes on the stack, but Fred does not actually contain any of the data related to this person. It doesn't contain the string Fred or anything like that. All it does is contains what is known as a reference. The actual person Fred that we created when we said new person Fred is allocated on the heap. And then in the variable Fred on the stack, that reference is a reference to the actual object on the heap. What's actually stored in there is a memory address, but in C#, the memory addresses are hidden away from us, and so we just call these things references, but that's what's going on. And that means when we write some code like, say, console write line Fred dot name, then the runtime mechanism has to look at that reference Fred, follow it onto the actual object on the heap, and get the data back from there. And you can compare that with if I say p1.x. In that case, the value of x is already there on the stack. So it's less of a journey to go and get the data with a value type than with a reference type, because it's immediately there rather than us having to go through. So we can see immediately that's one situation where we do get a performance benefit by using value types over using reference types. So we'll see later on there are pros and cons in terms of performance going both ways. In terms of deallocation, when we go through the close curly brace, then just like we saw before, the stack pointer will drop back down to where it started. And what that means is that the reference Fred on the stack is destroyed automatically. But you'll notice that the object of the type person on the heap still exists. And that is going to exist until the garbage collector kicks in and tidies it up. So whereas with stack objects, their removal from memory is pretty much instantaneous and again managed by the compiler, and that includes the actual reference Fred, but the object of type person could get tidied up a long time later when it comes to garbage collection. Something that's worth noticing here is that we've used the keyword new with both value types, structs, and with a reference type of person. And it's fairly obvious what it means when we come to the reference type, because another thing we could do here, if we simply said person Fred equals null, then we've created the reference, but we haven't created any object on the heap at all. So null just indicates that Fred does not contain any object, and then new is what actually creates an object on the heap. But clearly with a struct, new is doing something slightly different because we're not creating anything on the heap. If we were to miss off the new there, then what would actually happen would be we would have still allocated on the stack the appropriate amount of memory. So 32 bits for X, 32 bits for Y. But although the memory's been allocated on the stack, they would be uninitialized. And therefore, if we try to do something like we got down here, console write of p1.x, it's telling us that it's unassigned. So with value types, with structs, simply by declaring it, you do get the memory allocated, but you don't get any values put into it until you do the new to set it up, or maybe just directly set those values. Now, once we've got this idea established of the difference between value types and reference types, it has a number of implications, particularly when we're passing parameters and returning parameters. So, for example, if I just had a function here, so we'll just have a static void process person takes a person P, so that's a reference type, and then all we're doing here is say p.name equals Barney, and then out here, let's just get rid of that to keep things tidy, and so we create Fred, write the name, but if we then say process person passing in Fred, and then do the same thing again, then when we run that up, we'll see that Fred's name has actually changed to Barney, because what's happened here is we have only passed in the reference, so there's still only one object sitting on the heap, which is now referenced both by Fred in CreateObjects and by P in processPerson, and therefore when we change it through P, we see that change through Fred. And that's going to be the same whatever happens when you move references around. So whether you're passing them as parameters or returning them or whatever it may be. It's not quite the same when we're dealing with value types. So if I say static void process point, and then have a point, also P, just for confusion, and then we do something like p.x++, so we change the value. Let's do a console write of P in there, and then again, let's comment that lot out. And here we will do process point P1, and then do a console write of P1. Now in this case, we'll see that although we're getting that change, so the x++ changes it from 4 to 5, the actual original point P1 is remaining at 4. And that's because whenever you pass around value types, you get a copy. So P is a completely separate object from P1. It happens to be initialized as an exact copy, so it starts out with the value 4 and 5, but then when we do x++, we're doing it on the copy, not on the original, and so when we display the original, then we just get the original value. And so that's one of the big differences between value types and reference types. When you move value types around, you always get a copy. Whereas when you move reference types around, you're just moving the reference, the original object stays the same. Which again, as well as having behavioral implications, has performance implications, because clearly if your value type objects are quite large, have a large amount of data, then copying that data over starts to take up a large amount of time. Whereas with reference types, however big the object is, you're not moving the object anywhere, you're only moving the reference, and that's a fixed size. As we said, it's basically a pointer, so it's going to be 64 bits on most modern systems, maybe 32 bits on older systems. So if we consider the trade-off, our point is actually 2 integers, which is therefore 64 bits, same size as a pointer, and therefore it's not horribly inefficient. But once you get beyond that, you can see that all that copying around might start taking up time. So although in some ways we've seen that value types, structs are more efficient, we can see in other ways that reference types are more efficient. There is actually a way we can make value types, when we're passing them into functions, behave a bit more like reference types, and that's to use one or other of the keywords out or ref. But I don't want to get into that here. I will do a separate video on that, and I'll put a link from here when I've got that up. What I wanted to do next, though, was point out the differences that work along similar lines when we're doing assignments. So if we go back into here, if I simply here say something like point P2 equals P1, then the thing to bear in mind is we've still got 2 separate point objects that just happen to have the same values 4 and 5. So if we just print out P2 at that point, then we can see 4 and 5. But if we were to change P1, so again let's just do an x++ on there, and then print out both P1 and P2, and we can see obviously P1 has changed the x value to 5, but P2 has remained the same because there's no long-term linkage between them. Really, just the same as when we passed it into the function, the assignment is doing the same sort of thing. And when we deal with reference types, it's exactly the same as if we'd passed those into the method, which is to say we don't get a copy, we just move the reference around. So if I comment that out, and then let's have our person Fred, and then if we say person Barney equals Fred, what we've got there is two references pointing to the same object, because we haven't said another new person. And so now if we say Barney dot name equals Barney, then obviously enough, if we now print out Barney, we'll get Barney, but also if we print out Fred, we'll get Barney, because they are alternative references to the same object. Now in practical programming, you really don't want to do that at all because it's what's known as aliasing, having two names for the same thing. It's just confusing. But when you're passing into a parameter, then you've got to be aware that's what's going on, that P and the object out here, so Fred, they are just references to the same thing. We get a similar variation in behavior when we are dealing with comparison for equality. So if I were to have our Fred and our Barney, and then if we compare those, so if I just do a console write and then say Fred double equals Barney, question mark, and then equal or not equal, and then run that, we can see we're getting them as equal. And what we're saying there is simply we're testing to see whether both those references refer to the same object. So if I were to, instead of making them do that, if I were to actually make Barney a separate person in his own right, then we'll see that they're not equal because they're different objects. And even if they were different objects with the same value, so they're both called Fred, they're still different objects, and so they're regarded as not equal. So when we're comparing for equality or inequality with reference types, we're simply looking to see if they are the same object. Whereas if we do similar sort of thing with our points, and let's just do that like that, and then we'll take exactly the same code, or almost the same code, so change that to P1 and P2, we'll see actually, initially we get an error because you don't automatically get this equality operator, the double equals, for value types like we did for reference types. And that's because all reference types really behave in exactly the same way, whereas every value type is going to be different in terms of what the rules are for saying whether one object is the same as the other. So if we go to point, you can see I've already written these. So we've got a double equals operator for comparing 2 points, and also we've got a not equals operator for comparing the 2 points. And all the double equals operator does, and this is our design choice, we say that 2 points are regarded as the same if both their x value and their y value are the same. And here that double equals is just the built-in one for comparing integers. Not equals, we say they're not equal if either the x's or the y's are different. And so when we've done that, we can see that at this stage that's going to be equal because they both have 4 and 5, whereas if I change that one to something different, then they're going to be not equal. So with value types, we get what's known as value comparison. It actually looks at the individual values and compares them, though we have to write that for ourselves. Whereas with reference types, we get the reference comparison, where it simply looks to see if these two are referring to the same object. Now you can overload the double equals operator for reference types as well, but it's typically not a great thing to do. And in fact, this is one of the things we'll discuss in the video leading up to on this new record concept. but quite rarely done, but it is available. Now, if we want to do the similar sort of thing with a reference type, so if we want to have value style comparison on a reference type, then the thing that we're supposed to do is actually to not overload the double equals operator, but to write a method actually called equals. So here in our person, it's actually an override from something in the universal object base class. So we'll override equals. And then you can see that what we're comparing it to is actually being passed in simply as an object. So the first thing we're going to do is check whether that object is actually a person. So here we'd say person, let's call that other, equals obj as person. So that will try to convert it. If it fails to convert it, then other will be null. So we'll check for that. And if it is, return false. Otherwise, then we can just do our value-based comparison, which in this case is to say if our name is equal to other.name, then that would be what we judge. Again, we make up the logic for ourselves, but that would be what we have there. So here we'll find that those two are not equal because we're comparing the references and their different objects. But if I did Fred.equals, then we'd find that they're now equal because although they're different objects, they've both got the value Fred. Whereas if I change that one to Barney, now they're not equal because it's comparing the values. So with value types, we overload the double equals and the not equals if we want to do comparison. With reference types, we should leave the double equals alone, except in some very specialized circumstances we'll talk about, and we should instead override the equals. Now, all of that is how these things work. And I thought it was worth explaining how they work because that leads us into the decision we need to make as to whether the data type we're writing should be a value type or a reference type. And we can divide this decision into two sections. We can talk about the physical concepts, that's to say really performance issues and that sort of thing, but then also the design concepts because certain data types make more sense as value types and reference types. Now in terms of the physicality of this, the two considerations we've got to put together are these. One is the size of the objects and the other is whether that size is fixed. Now if the size of your objects is not fixed, then they have to be reference types. And by not fixed, I was mentioning things like arrays, which can have whatever length is chosen at runtime, and strings, which can have whatever length is chosen at runtime, things like that. Because remember, the stack memory allocation is all handled by the compiler. If the size of the objects is not known at compile time, then they cannot go on the stack. Another thing that keys into that is the idea of whether we've got inheritance. Because one of the features we have with structs is structs are not allowed to have inheritance. They derive from the universal base class object, but you can have no further inheritance than that. It's just not allowed. Whereas obviously with reference types we can, and we've seen it here because we've got these derived classes employee and customer. And you can see the problem. If I were to say person Fred equals and then new customer and then pass in Wilma and 3000, then we've got this issue. The size of a customer is bigger than the size of a person because customer has an extra field of credit. And although when we're looking at it here, clearly the compiler might know what's going on, in general, once you've got a base class reference, the compiler cannot know how big an object you're going to put in there and therefore can't allocate the memory, and that's why this sort of thing has to be done on the heap where the memory allocation is done dynamically at runtime, slightly slower but more flexible. And so that's what we've got with that. So if you need flexibility just in terms of the number of items, like with a list or something like that, or if you need flexibility in terms of inheritance, both of those cases you've got to go for a reference type. Whereas if it's fixed size, then the only consideration we've really got is how big is it? Because we saw whenever you move value types around, you're making copies, and the bigger they are, the slower that copying is going to be. We mentioned if the size of the struct, the size of the value type, is no bigger than the size of your pointer, then it's not going to be too inefficient. You can go beyond that. I wouldn't worry if it's twice as big or maybe a bit more than that. But beyond that, it's time to start thinking, is the performance going to be an issue? And again, that's something that is partially solved with this idea of a record that we're going to look at next time. So those are the two things, the physical, but then also this idea of the logical decision we have to make. What type of thing do we want to have as a struct? Well, the sort of thing we want to have as a struct is essentially fairly simple data types. The obvious one is if we say int x equals 4, and then we say int y equals x, and then we say y plus plus, clearly we don't want x to change as well, because these want to be separate entities in their own right. And we've seen that's what happens because they're value types. But we also saw that when you've got a reference type, then if I say person Fred2 equals Fred, and then I say Fred2 dot name equals Barney, then that, because there's only the one object, affects both of them. And clearly you wouldn't want that to happen with ints, but it does make sense that that can happen with classes like a person or a customer, where you might want to be able to change the name without changing the object. You certainly might want to say change the credit amount, even though we're not changing to a different customer. So that's where the decision is going to come. And I would say here that makes sense for a point being a value type, because if you've got a point and you copy it into another point, those points should be completely separate entities in the same way as our integers x and y are separate entities. They should not have any long-term relationship between them. And that brings us to another consideration, which is what we want to do with comparison. So if we have int x equals 4 and we have int y equals 4, then do we want to be able to say if x equals y, should that be telling us true or false? Well, in the case of integers, it makes sense that that should be true. We don't care that they're different variables x and y. What we care about is that they have the same value. Whereas if we had, let's just call that one P1 and then do another person P2. So we've got two customers, both called Wilma, both with a credit amount of 3,000. But if we say if P1 equals P2, I think we should still be regarding those as separate objects, and therefore this gives us back the result of false, because we might well have two customers who both happen to be called Wilma with the same credit amount. And when it comes to our points, I think they follow the same pattern as we have with integers. So if we've got a couple of points, and let's make them have the same x and y coordinates, then it seems to me it should be the case that those two are regarded as equal, even though they're different points. We're still doing a value comparison, and that's why it makes sense, additionally, for a point to be a value type. So that's what we had for the logical reason and the physical reason for choosing between reference types and value types. And for the most part, those two line up pretty well. So whatever the logical design decision is between structs and classes, also it comes to the same in terms of the physical of it. And in fact, in almost every case, the decision comes out to use classes, to use reference types. That's what we mostly write. The key reason being, because those things that are suitable to be value types, to be structs, are relatively limited, then most of them have already been written in some kind of library. So there's already various point classes in the graphics libraries and that sort of thing. And so, although it's a useful example, we typically don't need to write it for ourselves. Whereas the reference types tend to be things more that relate to our particular application area, and therefore we design those for ourselves. There is one class that we use very, very commonly where we hit a problem between this logical decision and this physical decision. And that is the string class. Because with a string, physically, it has to be a reference type because it's got this variable size issue. But conceptually, we want it to behave like a primitive type. So in just the same way as we saw here, where we said int x equals for int y equals x and then y plus plus, we don't want the two to affect each other. It should be the same with strings. So string s1 equals hello, string s2 equals s1. If we were to then change the value of s2 in some way, we don't want that to affect s1. And that's done with quite a lot of clever trickery. The first thing we have about this is that strings are what is known as immutable. So if we do something like s2.toUpper, for example, to make it uppercase, that does not change the value of s2 and therefore change the value of s1. It actually returns another string that we might call s3, which is the toUpper version. So although strings are reference types, they're immutable and therefore we can never have this sort of interference. And then the other thing that we have with strings is they are one of the few cases where for a reference type, overloading the double equals makes sense. So if we actually have a look at our person, you can see there I used double equals on a string, but that's not to determine whether those two are the same object, because they could be different strings even though those two strings have the same value. And so in that case, even though it's a reference type, the double equals for string has been overloaded. And that's something we want to be very careful of, but in the case of string, it makes sense because we've got this mismatch between the physical need for it to be a reference type and the logical need for it to behave as though it were a value type. And actually, that is what record is all about, because that gives us much better control when we're writing our own data types to have this compromise as to it physically being a reference type, but it logically being a value type. And we'll talk about that in the next video. So I hope you enjoyed that. Do like it if you enjoyed it. Do subscribe, and I'll see you next time for a good talk about records.